Welcome to section 6.4 in chapter 6. Let's talk about higher order graphing, but let's get an overall sense of the process before we jump into any one of the steps here. When we do higher order graphing, our first step is to assess the end behavior. Now, we've seen this before when we talked about x squared and x cubed. In fact, we even extended that to x to the even power and x to the odd power. But just to reinforce that here, if it's positive and x is even, both of our ends go up. Now, up is also the same as saying they both go to positive infinity. If it's even but negative, they're going to go to negative infinity. If it's odd and positive, right goes up, left goes down, or right goes to positive infinity and left goes to negative infinity. If it's negative and odd, right goes down to negative infinity and left goes up to positive infinity. Again, we've seen that before. Now, when we talk about higher order graphing, there's also things happening in the middle between the endpoints, if you will. And that's what we like to call turning points. And at most, the graph will have n minus 1 turning points. So if x was to the third power, you would have at most 2 turning points. If x was to the 7th power, you'd have at most 6 turning points. Then we assess the y-intercept. We've done that in every graph that we've done so far this semester. And then we worry about the x-intercepts, where y equals 0. Now, for us to be able to do that in higher order graphing, we've got to do a couple of things. We have to assess what are the potential values we can use for x-intercepts. That's called the rational zeros theorem. And then we've got to synthetically divide to figure out if these are zeros or not. And then finally, depending on the zeros that we find, it may give us what's called a multiplicity factor. And if it has a multiplicity factor, as in let's say we find that one of the zeros is 2 twice, then what happens is at 2, we're going to see this sort of graphing behavior. We're going to go all over all this when we actually get to the graphing, but I want to give you a sense of where we're going here, because the first thing that we're going to do that we haven't already done before is we're going to worry about the x-intercepts here. Now, we've done that before on the x squared when we could take and use the quadratic formula to solve for zeros, or we could solve by completing the square, or we could solve by factoring. But in these higher order graphing, we can't do that. So we've got to use synthetic division in order for us to be able to do that. So that's going to be our first step here, is we're going to do synthetic division, and that's going to lead us into the example that we're going to do first, example 1 here. But let's talk about synthetic division next. So let me clear this off here, and we'll bring in the synthetic division. What you're seeing on the screen is the steps that we take when we want to synthetically divide it. So let's go through each one of these steps, and then we'll actually do example 1 on page 468. To do synthetic division, the first thing we're going to do is we're going to arrange what's going in the house, aka the dividend, in order from greatest exponent to least exponent. As if this started with x to the 7th, we would go x to the 7th and the x to the 6th and so forth and so on. The last value in our descending order should be the constant term. Then we're going to draw a house. So when I call a house is that half of a rectangle that you see here. I call that the house. And we're going to put only the coefficients from the first step in there. So if we had 2x to the 5th plus 3x to the 4th minus 4x squared plus x minus 7, that's what we would put inside the house. We have to be careful, though. If we're missing a power, as you can see here, it went from 3x to the 4th to 4x squared, and what happened to the x cubed one? Where's x to the 3? Well, it's not there, and that's okay. Some problems just don't have that. But we account for that in our house by doing a 0 there. And then a quick tip to know if we've got the right number of values in the house is we look at the highest power and we add 1 to it. That should be the number of terms in the house. So if we started with x to the 5th, then we should have 6 terms, as in 5 plus 1 in the house here. And as you can see, there are 6 terms in the house, and that's where that 0 comes in for a long way. Step number 3, we basically draw a line from the numbers that we have. As you can see here, I've drawn a line, and we take the first number that's in the house and we bring it right below the line. For step number 4, we take the first number that's below the line and we multiply it times the number on the outside of the house. So in other words, in our case, 2 times 2 is 4. And as you can see in step 5, we take that number and we place it under the next number in the sequence here. So that 4 would go under the 3 in this case. And then we add those numbers together. 3 and 4 make 7. And then we repeat. We take 7 times 2 and then put the next number here. As you can see, that's 14. And then 14 times 2, which is 28. And then negative 4 and 28 make 24. And then 24 times 2 is 48. And then we take the 1 and the 48, and that makes 49. And finally, we have negative 7 and 98, and that makes positive 91. And then once we've finished with that, we assess. We ask ourselves, all right, is the last number 0? If the last number is 0, we just found an x-intercept. We just found a solution. We just found a 0 is sometimes what that's called. If not, then the number left over is the remainder. Like if you remember old school math, if you take 5 divided by 2, it doesn't go in there evenly. We might call that 2 remainder 1 in the old school days. Of course, we nowadays call that 2 1/2. But in the old school days, we might call that 2 remainder 1. So this 91 is a remainder. What it tells us is that this 2 does not evenly go into this polynomial. And this 2 really represents x minus 2. That's another thing that we need to talk about is what goes on the outside of the house. Essentially, it is one number, and it depends on the form that we're given. If they give us and say, hey, divide x plus 7 into something else, then the number on the outside of our house is the opposite of this plus 7. So again, we see the opposites coming into play here. So the number that we would use would be negative 7. So whatever it is in this form. However, if they say, divide 7 into the polynomial, then we're just going to use 7. So if they give us a number, we're going to use the number. But if they give it to us in the form of x plus or minus here, we're going to do the opposite of what they give us. So if they give us plus 7, we're going to use negative 7. If they give us just 7, we're going to use 7. So it all depends on what they're going to give us here. Let's put that negative 7 here so we're reminded us what to do. All right, I think we're ready to do example 1 now. So let's make these synthetic division steps a little bit smaller and clear some workspace for ourselves. Example 1 on page 468 says, if x equals 2 is a solution of x cubed plus 8x squared plus 21x plus 18 equals 0, then find the remaining solutions. All right, so in this form, what they've given us is x equals negative 2 is going to be on the outside of the house, or negative 2 is going to be on the outside of our house. We don't have to worry about changing that to the opposite because they didn't give us the form where we need to change it to the opposite. All right, and our dividend is already done in descending order. It goes from x3 to x2 to x1 to essentially x0 is what we like to call that one. It's also the constant term, and so that's already done in descending order. And the other thing that they told us is that this x equals negative 2 is a solution, meaning that when we first do our synthetic division, we should get a 0 at the end. All right, so that's good. It's kind of a reassurance. Let's set this up then. Negative 2 goes on the outside of our house. On the inside of the house is 1x cubed, 8x squared, 21x, and an 18. Again, notice how the x's did not go inside of the house here. We just put in the coefficients, and the coefficient to x cubed is 1. All right, then our next step says to draw the line. I think this is the hardest step. Kidding, of course. The 1 comes down, and we multiply. 1 times negative 2 is negative 2. We put that underneath the 8. 8 and negative 2 makes positive 6. 6 times negative 2 is negative 12. 21 and negative 12 makes positive 9. And 9 times negative 2 is negative 18, meaning that our last number here is indeed 0. That's what we expected to get. That's good news. That tells us that the work we did was good because it already said that negative 2 was a solution, meaning that we should get a 0 here at the end. But now it says to find the other solutions. So here's the thing we need to talk about is once you've done your synthetic division, what's left over here? Well, we know that negative 2 is a solution based on the 0, but what about this 1, 6, and 9? Well, anything below the line is going to be 1 power less than what we started with the first time, meaning that this number 1 represented x cubed. As soon as we did our division, everything below the line is 1 power less. In other words, this 1 represents 1x squared. This 6 represents 6x, as in positive 6x. And then this 9, there are no more powers of x left over other than x to the 0, so it's just plus 9. It still equals 0 from the beginning here, so that part hasn't changed. But now what we can do is this is a squared, and we know how to solve squares. We've done it before. We've done the quadratic formula. We've done completing the square. We've done factoring. I think this is factorable, and so that's what we'll do is we'll factor this to find the other two solutions. In fact, I think this is x plus 3 times x plus 3, or x plus 3 squared. Either way would work, and this tells us that x equals 3, and that means with a multiplicity factor of 2. Basically, it means 3 and 3. Rather than saying 3 twice, that sounds a little silly. We like to say 3 with a multiplicity factor of 2, meaning that 3 is on there twice as solution. And that's it. We just did our synthetic division, and we just found the other two zeros, which tells us that we could take the beginning here, this x cubed plus 8x squared plus 21x plus 18, and we could rewrite it in a slightly different format. And that format would be this, right? We know that x minus 2 is a solution, so that tells us that when we set it up here, we would have x plus 2, then we had x plus 3, and another x plus 3. And that is exactly the same as x cubed plus 8x squared plus 21x plus 18. Pretty cool how that comes into play, right? That we can take and factor this thing and break it down into its component pieces by doing synthetic division. Now, synthetic division is a huge step that we need in order to do graphing, because this is going to give us the x-intercepts again. Anytime we see 0, we've found ourselves an x-intercept, and that's what we're going to be looking for when we get to doing the graphing. Before we can do that, though, what we've got to decide in our next example is how do we decide what to put on the outside of our division bar in order to find potential x-intercepts.